All right, good morning. Okay, so what I'm going to do today is I'm just going to cover a topic of heat of vaporization. Okay, heat of vaporization is an important quantity when it comes to the boiling point of a material. So if you recall, what we said in section 11.1 is that you have these intermolecular forces, right? Which are attractions between molecules or atoms. And what we said was that there were attractions that you can get between polar molecules, right? And so these molecules are attracted to each other. Now, it's not necessarily rigid. They may still be moving around, but on average, they're attracted to each other. And it's really just electricity, right? It's the opposite charges kind of idea. So the more polar these substances are, the stronger these intermolecular forces. We said there was also a type of force called London dispersion forces, right? These dispersion forces were for materials that don't have like a permanent dipole. So you might have like neutral atoms. They're still attracted to each other because of random fluctuations of their electrons. It's a quantum mechanical phenomenon. So they're attracted to each other. So in general, molecules are attracted to each other. Atoms are attracted to each other, even without chemical bonding. Even if they're not chemically bound to each other, they're still attracted to each other through these forces. Now, when we consider the difference between, let's start with a solid. You know, you take a piece of solid, like a piece of metal, right? A piece of metal, there's a bunch of atoms in there, and they're all like rigidly held together, right? They're all stuck together. So there's very little motion occurring in those atoms, really just vibrational. They're just vibrating with respect to each other. And so it's a very rigid type of structure. So what we can do is we can start adding heat, right? And eventually what will happen is you'll melt it, right? And so now you'll end up with a pool of liquid, right? Now that could be liquid mercury, for example, or it could be some other liquid, you know, molten metals, like when in a foundry, when they're making steel, right? That's liquid metal, okay? So now you got a liquid. And now what's going on? Well, the molecule or the atoms, in this case, since it's a metal, the atoms are, you know, they're near each other. They're still very close to each other. The density of a liquid is pretty close to that of a solid. They're pretty much the same. But they're able to move around. The atoms are able to flow with each other, right? Think again of liquid mercury. You can flow it, you know. So there's much more motion capable in a liquid than there is a solid. But you can keep going, right? You can keep adding more and more heat. And what happens? Now it turns into a gas. And, you know, we're probably not used to that, you know, because metals tend to be solids at room temperature, but at extremely high temperatures, metals will vaporize, right? We call this vaporization. Okay. They will vaporize into a gas. Okay. So what we're interested in here is the idea of this vaporization, what's going on in terms of vaporization. And we're not going to focus for the solid liquid transition right here. We'll focus on the vaporization transition, okay? Now notice when a liquid vaporizes into a gas, now the atoms are able to move very far away from each other. In fact, so far away that they're not even really interacting with each other. Remember PV equals nRT when we talked about gases? One of the reasons that PV equals nRT works is because the molecules, the only way they interact with each other is through collisions. They're not really attracted to each other at all anymore because they're moving so quickly At high temperature, the speeds are really high and they move away from each other. They just collide, just random collisions taking place, okay? So intermolecular forces in the gas phase, intermolecular forces are essentially zero, right? There are no intermolecular forces. They're just moving around doing their own thing, okay? If they happen to get in each other's way, they collide, but they're not attracted to each other. But in a liquid, there are intermolecular forces. They're greater than zero, right? So what vaporization does, in a sense, is it is a way of measuring how strong the intermolecular forces are. If there aren't any intermolecular forces in the gas phase, and there are intermolecular forces in the liquid phase, then looking at that phase change, that phase transition, that will give us some insight into the nature of the intermolecular forces. And that's actually one of the ways that we figured out the types of intermolecular forces that exist and how strong they are, is by looking at vaporization. And it's a whole analysis that we can use, and we're just going to look at a little bit of it here today, but it's very, very powerful. So in a sense, what we do, or what we can do, is we can measure, one thing we can do is we can measure the boiling point. Of a liquid. Okay. And that will give us a sense of the strength of the intermolecular forces. And we would generally say that as the strength of intermolecular forces increases, the boiling point increases. In general, that's pretty much true. So for example, let's take liquid helium. Okay, helium in liquid. The boiling point is 4 Kelvin. That's pretty low, right? It's not zero, but it's pretty close to that. Now, the assumption here is that there's a certain pressure this is being measured at, but we won't worry about that. Let's take, for example, liquid nitrogen. Oops, sorry, liquid nitrogen. The boiling point for liquid nitrogen is like 77.4, I think it is, Kelvin. So that's much higher than it is for helium, but it's still pretty low, right? That's still very low. Let's consider, for example, water. Liquid water. Its boiling point is 100 degrees C, which is 373 Kelvin. Maybe it's 373.15, but whatever, 373. That's pretty high. And then just one that I happen to remember, sodium, liquid sodium, that's a metal. That one is 1460. Oh, I'm sorry, sodium chloride, not sodium, sodium chloride. 1465. Oh, I'm sorry, that's 1465 Celsius. So 1765, around 1740. Okay, that's a lot higher there, right? So what we would claim from this data set is that in terms of the strength of the intermolecular forces, these would be the strongest. Now, why are they the strongest? Well, they're ionic. These are ionic bonds that we're talking about. Ionic bonds can be pretty strong. This would be the second strongest. Now, remember, this is hydrogen bonding, right? Water has hydrogen bonding. Those are pretty strong intermolecular forces. The third one would be the third strongest here. This would be nitrogen. This one is dispersion forces. Why? Well, remember, this is just N2, so there's no polarity. The electronegativity of the atoms is the same, so there really is no dipole. So it's just got to be dispersion forces. Of course, the other ones have dispersion forces too, but I'm just writing down the strongest form, the most important intermolecular force for that substance. And then this one is the weakest because it has the lowest boiling point. And this one, again, only has dispersion forces, but these dispersion forces are really weak because the helium atom only has 2 electrons. And remember, the dispersion forces increase in strength as the number of electrons increases in the substance. So nitrogen has 14 electrons, helium only has 2. Nitrogen has 14 because there's 2 nitrogens, each has 7. And so there you go, those are your intermolecular forces, okay? So we can use it that way. Now we can also measure the amount of energy in the form of enthalpy required to vaporize, to boil 1 mole of a liquid. Okay, we can also do that. We can measure how much heat it takes to boil off a mole of a liquid. So this is called the heat of vaporization. Okay, and the symbol for it is typically delta H with a subscript VAP. It could be VAPOR. You could even write out the whole thing. It just depends on who's doing this. But notice it's delta H, and the units are typically kilojoules per mole, just like we've seen with all of the other enthalpies. Okay, so at constant pressure, we would use delta H, and delta H vaporization in kilojoules per mole is the heat of vaporization. That is the amount of energy, the amount of heat required to vaporize a mole of a substance. Okay, so let me see if I can find for you here some values. Okay. Those are terrible units. Something you have to be careful about these because sometimes people will put the units in per gram as opposed to per mole. So I'm just going to go here and look in. Here we go. So let me stop sharing. Okay, here we go. All right, these are heats of vaporization, right? So you could call it enthalpy of vaporization or heat of vaporization. We use both terms, okay? And these should be in kilojoules per mole. So I think these are in the same units, okay? So if you look at, let's take helium, for example. I was talking about the very low boiling point of helium, right? Look how small that is. That's, 0.08. That's a pretty small value. Notice as you go down the column, the values increase. They're increasing because there's more and more electrons, stronger and stronger dispersion forces, right? More electrons means stronger dispersion forces. So that means the attractions are stronger, which means that they will boil at a higher temperature, but this energy of vaporization will go up. So the heat of vaporization for krypton, for example, is 9, which is quite a bit larger than it is for helium, right? 0.08. That's a difference of over 100. So it's 100 times the amount of energy required to boil off a mole of krypton. If you look at the metals, they tend to be very high because the intermolecular forces in metals are what we call metallic bonds. We haven't talked much about metallic bonds in here. It is a topic in the next chapter, but we haven't covered that. But if you take a look, those values are in the hundreds. It takes a lot of energy to boil off, to vaporize metals. Mercury might be a little bit lower than some of the others, right? If you take a look at Mercury at 59, remember, mercury is a liquid at room temperature. It's not a solid. So it's already kind of getting closer to being a vapor or being a gas at room temperature. So we would expect that maybe it doesn't take as much energy to boil off mercury as it does other metals. And you can see that's true, right? 59 is an outlier. That's really low compared to, say, gold, which is 334, or even platinum or platinum, which is 510. So that's one of the reasons that mercury is somewhat of a dangerous metal, is that it becomes a vapor much more easily than the other metals do. That means you can breathe it in through your nose, right? It can go into your sinuses and then go into your blood system. So there's a danger in that, in that, you know, these metals, generally we're not evolved to have metals like that in intake those. Okay. Notice hydrogen is pretty low as well, 0.44. But again, the metals much higher as you go up here. And there's some outliers in there and everything. But there you go. Okay. So that's a group. Here's another group. These are organic substances with water in there as well. Or these are some things that you might think of as typical liquids. Acetone, for example, is sometimes used in nail polish removers. So sometimes when you are playing around with nail polish removers, you might smell the acetone. It's not really very good for you, but not as toxic as something like mercury. So here's the boiling point in Kelvin. Here's the boiling point in Celsius. Here's the boiling point in degrees Fahrenheit. And then here's the heat of vaporization in joules per mole, not kilojoules per mole, but joules per mole. 31,300, so that's 31.3 kilojoules, right? Here's aluminum, a metal, right? A metal is going to be higher because of those strong metallic interactions. Acetone, by the way, doesn't have a hydrogen bonding. It has a dipole moment. So it's dipole-dipole interaction. So it's 31.3 kilojoules per mole. Diethyl ether also has a dipole moment, but a little bit weaker than acetone. Butane is non-polar. So it's really just dispersion forces. But butane has a lot of carbon atoms and a lot of hydrogen atoms. So it does have some pretty strong dispersion forces. But you can see it's weaker than, say, acetone, which is polar, or diethyl ether, which is a little bit less polar. Get to ethanol. Ethanol has hydrogen bonding. So now you jump up to about 38 kilojoules per mole. I'm not sure what this parahydrogen is, to be honest with you. It's just hydrogen. Hydrogen is very small, 899.89 kilojoules. Iron, very high. It's a solid at room temperature, right? It's a metal. And then isopropyl. Let's look at water. Water is around 40.6 kilojoules per mole, or 40.7 kilojoules per mole. Okay. So water, with its pretty strong hydrogen bonding, is, you know, pretty high in terms of like the substances we think of as being liquid at room temperature, but significantly lower than things that are generally solids at room temperatures, like metals or salts or things like that. Okay. So that's the heat of vaporization, okay? And the connection there with boiling point and the strength of the intermolecular forces, that's essentially what we're looking at there, okay? So now let me come up, and I'm going to bring up a problem. Oops, sorry, wrong one. Yeah, I'll show you this one. There we go. All right. So this one, let me just bring this up so I can see it. There we go. This one shows the vapor pressure of 3 different liquids and how they vary with temperature. Okay, so the liquids are named here. Tetrahydrofuran, which is a relatively common organic solvent used in organic chemistry. Trichloroethylene, which is an industrial solvent. And then ethanol, which is the main, that's the alcohol that is in things like wines and beers and liquors and things like that. Okay. So notice what's going on here in terms of these three graphs. Let's come down here to temperature 50 degrees Celsius. Okay, so 50 degrees Celsius is pretty hot. That is what? 90, about 120 degrees Fahrenheit. Okay, so that's pretty hot. Notice the vapor pressure of the tetrahydrofuran is around, looks like it's around 440 torr. Remember, an atmosphere is 760 torr. The vapor pressures of the other two liquids, trichloroethylene and ethanol, are lower, much lower, around 220 maybe. So this is 220, this is about 440, just reading on the graph there. It looks like each division is about 0.2. I can actually expand that, right? So you can see that a little bit better, right? So here's 200. That looks like they're starting off close to 220. This is 400 here, 420, around 440. I would estimate it about 443 or 444, something like that, okay? So at that temperature, the tetrahydrofuran has a larger vapor pressure, okay? So what does that mean? What's the connection here between vapor pressure and temperature, okay? This is a very common graph we use in the sciences, in the physical sciences. The graph of pressure and temperature is often used to discuss how a particular substance behaves, and that can be used for all sorts of purposes. So let's come back. What I'm going to do is I'm going to show you a little bit, or come back, review a little bit about vapor pressure. I'm not sure what the best symbol for vapor pressure is. I think Alex uses a V. Okay. Sometimes people will use P vapor. Okay. Whatever symbol you want to use. Okay. The idea is this. Imagine, we'll just assume we're dealing with liquids. Solids generally have very low vapor pressures. So imagine you got a beaker, a container, and then you've got a liquid. Okay, so here's our liquid. What will happen is some of the surface molecules will be essentially kicked out of the liquid by the molecules underneath them. They just smack into each other. Remember, so this is a liquid. So they're bouncing around, colliding with each other. If you're a molecule at the surface and something hits you from underneath, it may hit you with enough energy that you escape the liquid altogether. And so it might go off into space here, right? Now, in general, what could happen is it could just keep going and leave, or it could bounce around, maybe collide with a molecule in the air and then come back into the liquid, right? So it might just jump back into the water or the liquid, whatever kind of liquid you have. But if I do the following, if I put a little cap on here, okay, so I'm going to close off this surface. What that does is it traps all those gas phase molecules inside the container. They can't escape the container. So that means that those molecules have two possibilities. They can either be down here in the liquid phase, or they can be up here in the gas phase, right? Close these. Okay, so they can be either one. What you'll find is that over time, it will come to what we call equilibrium, an end point, where you'll have a certain number in the gas phase and a certain number in the liquid phase, okay? Now we can measure, since this is a gas, we can measure the pressure of this vapor. And we call that vapor pressure. And what that graph is showing us, there's a couple things you can get out of it, but for now, we'll just focus on one of them. What it shows us is that as you increase the temperature of the liquid, the vapor pressure increases, and it generally forms a curve that looks something like this. So the higher the temperature is of the liquid, the greater the vapor pressure above the liquid is going to be. So that vapor pressure is, in a sense, a measure of the pressure of the molecules that come from that liquid. So we're not measuring the pressure of the liquid itself. We're measuring the pressure of the gas that's above the liquid, and that pressure increases with temperature. Okay, it increases in a particular mathematical form that I'm not going to worry about you don't have to worry about right now. It's a type of exponential function, and it's something that if you go on to take Chem 12, you'll look at those kinds of functions in that course. Okay, so that's kind of cool. So, this temperature here could be anything. This might be 50 degrees C, like it was in that other curve. It might start at 100 degrees C. It might start at -50. It's just depending on who made the graph and what it's showing you. But the point is, notice that you can have different starting points and you can have different curves, even though the shapes look kind of qualitatively the same. They may not start at the same point, and one might increase more rapidly. Actually, that's probably not very good. One might increase more rapidly than the others, right? If you look at this one at the top here, let me put it in different color. This one at the top, it starts off at a higher vapor pressure than the other two do. It starts off higher, but it also increases more rapidly. Remember the slope, the idea of the slope. So if you have a line that goes horizontal, the slope is 0, right? So if you have something that goes like this, the slope here is less than it is here, right? There's a slope right there, which is higher than that one is right there. Not by much. They're pretty close the way I drew them. But this one starts off higher and it has a higher slope, okay? Now, in general, what we do is we say the following. The heat of vaporization is related to the strength of the intermolecular forces. The weaker the forces, the higher the vapor pressure is going to be, right? So let's come back and remind ourselves. Weaker intermolecular forces result in lower heat of vaporization and higher vapor pressure. Because the idea is if these molecules are holding on to each other very tightly through intermolecular forces, they're not going to allow many molecules to go into the gas phase, so the vapor pressure will be low. On the other hand, if you have stronger intermolecular forces, these will result in a higher heat of vaporization and a lower vapor pressure. Okay, does that make sense? So let's do both cases. Weaker intermolecular forces, they're not holding on to the molecules very tightly. So some of them are going to go, a lot of them are going to go into the gas phase. So you'll have a higher vapor pressure. But also, the heat of vaporization is the amount of energy required to put a mole or a gram, depending on your units, a mole of this liquid into the gas phase. So the weaker the intermolecular forces, the less energy it's going to take. So that's right here. Weaker intermolecular forces result in a lower heat of vaporization, but a higher vapor pressure. So from these graphs, you can gain some insight into vapor pressure, into boiling point, into heat of vaporization, and then into the strength of the intermolecular forces. So you can get all of that out of these curves, okay? There's a way to get the boiling point as well. Now, let's take the opposite, stronger intermolecular forces. They're holding tightly onto each other. They're really strongly attracted. They're not going to allow many molecules to go into the gas phase. They're going to stay in the liquid phase. So you're going to have it takes a lot of energy. The temperature is going to have to be very high to get those things into the gas phase. So you'll have a very high heat of vaporization, but also a low vapor pressure for a given temperature, right? So for this temperature, let's just pick this one arbitrarily. This one has the lowest vapor pressure, right? Because the vapor pressure is right across here. That's the lowest vapor pressure. This one here has a higher vapor pressure. It's right there. And this one has an even higher vapor pressure, which is right there. So we would claim that the one at the top has the weakest intermolecular forces, and the one at the bottom would have the strongest intermolecular forces. You can listen to this a couple times if it's confusing, but pretty much that's the way it works. So let's take a look at that problem now. We've done enough of it to be able to, I think, enough to be able to look at it. Okay. This graph shows the vapor, or how the vapor pressure of three liquids varies with temperature, right? Remember, higher temperature means more energy, or a greater amount of energy. So the vapor pressure of the three. So let's answer some of these questions. Which liquid is the most volatile, and which one is the least volatile? Now, very often people don't know what that word means. You know, we often use volatile in an everyday sense to mean explosive, right? We would say that a person is quite volatile. They just will explode at, you know, the smallest of difficulties, right? But that is an incorrect interpretation of the meaning of that word here. When it comes to the technical meaning of volatile in this context, volatile means more gaseous. So if something is more volatile, it's more gaseous. And if it's less volatile, it's more liquid or solid-like. So which one is the most volatile? Well, that's going to be the one that is the highest vapor pressure, right? The most gaseous is the highest vapor pressure. So the tetrahydrofuran at any given temperature on these curves, so let's take 60 degrees Celsius, it has a vapor pressure of 640 torr. That's a little less than an atmosphere, right? Remember, an atmosphere is 760. The ethanol is in the middle, and then the trichloroethylene at 60, it has the lowest vapor pressure. So the trichloroethylene would be the least volatile. The one that has the lowest vapor pressure would be the least volatile. Okay, so most volatile, THF, we call it, tetrahydrofuran. And then trichloroethylene, I guess people call that TCE. I'm not sure if they do. That one would be the least volatile, and then ethanol's in between. Okay. What is the normal boiling point of each liquid? Note, your answer must be within 1 degree C of the exact answer to be graded correct. Okay, the normal boiling point. Okay, so here's what we say in terms of that. The normal boiling point is the temperature that something is rapidly converted, undergoes a rapid phase change from liquid into the gas at normal pressure. Normal pressure is 1 atm or 760 torr. So all you have to do is look at 760 torr, okay? and read off the graph what that temperature is. Okay, so I'm going to do it here for the THF. For the THF, 760 is your vapor pressure. When that pressure is equal to the atmospheric pressure, that's called the normal boiling point. That appears to occur at 65 degrees, right? Okay, so I see why they're making you be within 1 degree C, because each line is only 1 degree, so you don't even have to really estimate very well. So when you get up to 760, the temperature looks to be 64. So we would say the normal boiling point of this liquid is 65 degrees Celsius, right? 1, 2, 3, 4, 5, yeah, 65. That's the normal boiling point. The normal boiling point of water is 100, right? Okay, so of each liquid, so let's do the trichloroethylene. Well, again, really, we're going to do it at 760. The boiling point is the temperature that something boils at, right? But it's also the temperature when its vapor pressure is equal to 760 torr. So 760 for the ethanol. I'm going to do the ethanol here because it's in the middle. The ethanol, that one is right here. So it reaches 760 here, right? See how far out that is to reach 760? That occurs at 78 degrees Celsius. And that's right, it is 78. Okay, I remember that one is 78. Now the trichloroethylene, that gets its 760. See what I'm doing? I'm just bringing it onto the trichloroethylene, and I'm going to go up to 760. There we go. 760 there occurs at 87. You know, to be honest with you, it looks like it's around 86.9. But I'm sure that you would get the correct answer if you put 86.9. So around 87 there. So that one has the highest boiling point. So if the question was which one has the highest boiling point, it would be that one right there. Okay. That means stronger intermolecular forces, right? Let's see. I'm gonna have to make this a little bit smaller so I can read the third question. Suppose a beaker of trichloroethylene, that's the green one, is put inside a sealed tank containing trichloroethylene at 57 degrees C and 275 torr. After 10 minutes, will there be more liquid in the beaker, less liquid, or the same amount? Okay, so here's the picture they're saying. Let me draw a picture of this. Trichloroethylene. What they're doing is they're saying, look, you got this tank, and we're going to put the liquid in there. Okay, so you got your liquid. It already had some gas in it. You know, it already had the gas, and the pressure was 57 torr. Okay, the question is, when you mix this liquid with that gas, will you get a higher vapor pressure after, a lower vapor pressure, or it won't be any different? And so here's what I'll say about that. The vapor pressure is a function of the temperature. So vapor pressure is a function of temperature. Okay. What that means is it doesn't matter how much we start off with. We could put any amounts in and we will end up with the same vapor pressure. As long as there's enough to actually, you know, you have enough of the substance to fill the container. And since we started off with, you know, enough gas to have 57 torr, we'll get the same answer. So the answer here is that once the container, or let's call it the system, reaches equilibrium, which is in a sense your end point, the vapor pressure will be dependent on the PT curve. Okay, the PT curve, the pressure temperature curve, is what will tell you what the vapor pressure is. So you just read off that curve. So let's go take a look at that curve. Okay, 57 degrees C. So here's, oops. So we're doing the trichloroethylene, which is the green one. So here's 57. So at 57 degrees C, it looks like the vapor pressure is a little under 280. Yeah, is that right? Because those are going by 20s, right? So 57. Oh, I'm sorry. Yeah, it's 220, 240, 260, 280. So a little under, just a hair under 280. It looks like it's around 279 or something like that. So let's see. They say, oh, that's a little tricky. They say it's 275. And then this says that it's 278. Boy, is that the same pressure or different? That's a little tricky. They're being really tight on that. So let's come back over here. Oops. There we go. So I'm going to come up here to 57. For some reason, it's not clicking very well, unfortunately. Sometimes I guess that happens. Okay. So 57 is right here. Gosh, it looks like it's right on that line. And then that would be 280. So it actually looks to me as though it went up a little bit. It went up a tiny bit. It's pretty close. So you just have to kind of judge that, whether they think that it went up or not. But the curve for a given temperature will tell you what the vapor pressure is. So if they say it starts off at this pressure, you just look to see what the end pressure is. Oh, there we go. Well, if I stop sharing and share again, maybe that'll help a little bit better. Oh, I know what's going on. There we go. I'm sorry. So let's come back to 57. Man, that's, it's pretty close, right? Like that's probably 275. That's probably close enough to 275 that it didn't change. So your answer would be that it didn't change. Okay, because they're saying it's 275. Yeah, the curve is what will tell you what's going on.
So the time that they're putting there is irrelevant.
Right. The time should be, well, I mean, there's no time. I didn't see any time. Oh, after 10 minutes.
10
Oh,
minutes.
you're right, after 10 minutes. So the reason they're saying after 10 minutes is they're trying to say that there's enough time for it to equilibrate. If you have a tank with gas in it, within 10 minutes, it should stabilize. As opposed to, say, 10 seconds, where it might be not enough time to mix things together. Okay. So let's take a look at this one right here. It says 788 at 82 degrees C. So let's see at 82 degrees C. So, oh, I'm sorry. You have to really read it carefully. So this one, they're asking for isopropyl acetate. So isopropyl acetate, again, is the one in green. So here they want it within 82 degrees and then 788. So 82 is like right there. That shows up as 600, right? If you look at the red line, it's, when you're at 82, it's 600. So this one, they said 788, right? So that means it went down, right? If you fill it up with 788 torr, but then you put the liquid in there and stabilize it at 82 degrees C, then it's gonna go along this curve. So that means it went down because at 82 degrees C, the vapor pressure should be 600. And so if it started at 788, went down to 600, that means it decreased. Okay, that one's a little easier. The other one was a little trickier.
So since it's
Yeah.
decreased, does that mean that there is now more liquid?
That's right. There'll be more liquid, but
Okay.
maybe not that much more because, you know, a liquid is 1,000 times more dense than a gas generally. So it takes, you know, like if you lose 99% of your gas, the liquid only goes up by like, you know, 1%. So it's not much of a difference, right? But yeah, it would go up. It would go up. That's true. Okay. So let's see here. Okay, let's take a look at this one. All right, understanding the connection between vapor pressure, boiling point, and the enthalpy of vaporization. So again, vapor pressure, the amount of the material that's in the gas phase, the boiling point, the temperature it boils at, and then the enthalpy of vaporization, how much energy it takes to convert a mole of the liquid into a mole of gas. Okay. So use the observations in the first column to answer the question in the second column, okay? So at -4 degrees Celsius, substance E, I don't like this problem in a sense because I don't like E and F and E. I'd like to see some real compounds, but that's fine. E has a vapor pressure of 83 torr, and F has a vapor pressure of 33 torr. So they're at the same temperature, right? And remember the curve, that what the curve shows us is there's a relationship between vapor pressure and temperature, okay? And so these are at the same temperature. So imagine those two curves being at the same temperature. So on the x-axis, they're the same. E has a higher vapor pressure, right? It's 83. F is a lower vapor pressure, 33. The relationship between vapor pressure and enthalpy of vaporization is that if something is more gaseous, more volatile, it has a lower heat of vaporization. So the one with the higher vapor pressure will have the lower energy of vaporization, enthalpy of vaporization. The one with the lower vapor pressure will have a higher enthalpy of vaporization. So in this one, they're asking for the higher value of enthalpy. So the higher enthalpy would be the one that's 33, which would be F. F would have a higher enthalpy of vaporization because less of it is in the gas phase at that temperature. At 1 atm pressure, substance C boils at 41 degrees Celsius. D boils at 76 degrees Celsius. So one's boiling at a lower temperature. Lower temperature, boiling at a lower temperature, means that the intermolecular forces are weaker, right? If something boils at a low temperature, that means that it's not being held very tightly. So vapor pressure tends to go up more rapidly with ones that boil at lower temperatures. Again, come back to those curves. So the idea, we'll come back to this in just a second. So here's T, here's your P. So one substance does something like this, another substance might do something like this. Okay. Okay, so what we're saying then is once they reach 760, and I'm just putting 760 up here just so that we've got that, this would be the boiling point. So notice the one that has the boiling point there, 760 for this one is all the way over here. This one's going to have a higher boiling point. Okay, so the one that has the higher boiling point, that one in general have a lower vapor pressure, right? This curve right here is always lower than this one. This one's always higher. So the one with the higher vapor pressure has the lower boiling point, right? So that's that relationship. So when we answer that question, which I guess is part B right here. Okay, the one that boils at 41, that's the lower, that's going to have the higher vapor pressure. So substance C would have the higher vapor pressure. Okay. And then the enthalpy of vaporization of A is smaller than B. Okay, so this one, A, is going to boil at a lower temperature because it has a lower heat of vaporization. So which one has the higher boiling point? Well, the one with the larger heat of vaporization is going to be B, right? You have to read it carefully. The enthalpy of vaporization of substance A is smaller. Well, that means the enthalpy of vaporization of B is larger. So the one with the larger heat of vaporization is going to have the higher boiling point. Okay, so that'd be substance B. Okay. Let's see if there's another one in here. There we go. Let's take a look at this one. I haven't, some of these I haven't seen. So they're kind of interesting. Okay. Calculating the vapor pressure from boiling point and the enthalpy of vaporization. Okay, now this is an interesting problem. This one is the actual calculation. And this one says that you're given the enthalpy of vaporization for substance X, and it's 25 kilojoules per mole. And then the normal boiling point is 87 degrees C. Calculate the vapor pressure of X at negative 93 degrees C. So at a completely different temperature, right? So notice they're giving you some information here. So let me take that off. Let's come over here. Here we go. Sorry, hold on a second. So this is called the Clausius Clapeyron. I can never spell this guy's name. Clapeyron equation. And what it says is the natural log of the ratio of two pressures, P2 over P1, is equal to minus delta H vaporization over R times 1 over T2 minus 1 over T1. Okay, so R is the gas constant. Okay, and that's 8.314 joules per K mole. Okay, T1 and T2 are in Kelvin. Okay, so P1 and P2, these are vapor pressures. Okay, so that's called the Clausius-Clapeyron equation. And let me see, let me come back over here. Okay, so in this particular problem, they tell us that substance X, the delta H of vaporization, is equal to 25.0 kilojoules per mole. Okay. And then they tell us the normal boiling point is 87 degrees C. You know, okay. And then they want you to calculate the vapor pressure at negative 93 degrees C. I see, they put a little dot there. Okay. All right, so there's our information. They want you to round the answer to 2 significant digits. Okay, so here's how we use the Clausius-Clapeyron equation here. we have the heat of vaporization right here. That's right here, 25 kilojoules per mole. So we know what that is. We have the value of R here, 8.314 joules per K mole. So we have that there. Although there is an issue with the kilo, right? You know, the heat of vaporization is in kilo and R is just in joules, kilojoules versus joules. So we'll have to take that into account. We have two temperatures. So we have a temperature is 87 degrees C, which is not in Kelvin. We have a temperature that's negative 93, which is not in Kelvin, but we can convert those to Kelvin. So we have a couple temperatures. So everything on the right side is there, right? We have everything on the right side. The way this problem's set up is kind of nice. Now, what we're asked to find is the vapor pressure at negative 93. So what's the vapor pressure? Well, there's two vapor pressures here, P2 and P1. So which one do we want? Which one we call P2 and which one we call P1 is actually our choice. We can call one 1 and the other one 2. But it doesn't look like any pressures are given here. So it looks like you got two pressures, but we weren't given any of them. And we're asked to find one. So how do we find it? It turns out in this problem, we were given one of the vapor pressures. We may not recognize it though. When it says the normal boiling point is 87 degrees C, which is right here, the vapor pressure at the normal boiling point is 760 torr. Remember that? It's 760. So we were actually given the vapor pressure at 87 degrees C. Now what we want to do is we want to figure out what that vapor pressure is at negative 93. So that Clausius-Clapeyron equation allows us to do that. So what I would recommend for this one is, since we want to find one of these pressures, if you look at it mathematically, the one at the top would be easier to calculate because, like if I said, hey, x equals 1 over a, or let's do it this way, x equals n over a. And I want to find a, I have to go through some algebra to figure out what a is. On the other hand, if I have x equals, a over n, and I want to find a, this would be easier to find a algebraically than this would be, right? Because here you have to do 2 steps. Here you just have to do 1 step. So what I would recommend is the pressure they're asking you to find, make that P2. So we're going to say this is P2, and that occurs here at this temperature. So we're going to call this T2. And so that means this would be P1 and this would be T1. Okay, so I'm going to make a little table down here just so that we have it. So delta H is, I'm going to go ahead and put it into joules. So it's 25 kilojoules, so that'd be 25,000 joules per mole. Your R is 8.314 joules per K mole. Okay. Your T1 is 87 plus 273, which is 360 Kelvin. Your P1 is 760 torr. And then your T2 is negative 93. So when you add that plus 273, you get, what is that, 180? So T2 is 180 Kelvin. And then we want to find out what P2 is.
Are the pressures like stable values at certain temperatures? I'm not sure where 760 torr comes from in relation.
So that was in the earlier problem. Remember where we had to read off the graph and find the normal vapor pressure?
But wasn't that only just for one of those, for a specific substance?
Every substance has a normal boiling point at 760 torr. So what we did was we looked at all 3 graphs and we went up to 760 and then read down to find the boiling point, right? So 760 is the key number there. That's called the normal boiling point. The normal boiling point is the temperature that something boils at, but it's also the temperature when it reaches 760 torr. Okay.
Okay, and it's not specific to, okay. Thank you.
Non-specific, exactly.
Okay.
Exactly. Okay. So it looks like since I already went through and put these into Kelvin, right? 180 Kelvin and 360 Kelvin, that part of the equation is done. I've taken into account, the kilo, so they're both in joules per mole. So that's taken into account. That will give us the left side of the equation, and then that's going to be equal to the right side of the equation, right? So we have everything we need over here, okay? And then that will give us what we have over here. So let me just go ahead and calculate the right side of the equation. I think I can. I don't know. I guess we'll just do it this way. Okay, I put everything in that little box there. So I'll go ahead and make a little more room in here. Okay. All right. ln. Okay, so we're not dealing with the left side yet. Well, I'll come back to that in a moment because there's something in here you may not be familiar with. So minus, don't forget the minus, 25,000 joules per mole divided by 8. I guess I should put this in parentheses because I got that negative in front. Sometimes it just seems awkward for me to have a negative in front. So I'm going to put that in like that. Take a look at the units here. They don't exactly cancel. The joules cancel. The moles cancel, but the Kelvin doesn't cancel. But that's okay because we've got Kelvin in here that's in the bottom, in the denominator. So that will cancel. So 1 over T2. So that would be 1 over, T2 is 180. Minus 1 over T1. So 1 over 360. Okay. So, this is where you want to pull out that calculator because I'm not very good at taking differences of reciprocals unless they're very simple numbers like halves or quarters. So I'm going to do the reciprocal of 180 minus the reciprocal of 360. And is that right? That can't be right. 180 reciprocal minus 360 reciprocal. There we go. So that's going to be equal to, let me go ahead and put the negative here. And then this would be 0.00278. And then this is 1 over Kelvin. So 1 over Kelvin is typically written as Kelvin to the -1. Okay, because it's 1 over Kelvin. Now let me do the 25,000 divided by 8.314. And you got, it looks like it's 3,000. So 3007. I'll just put that in there. And then you've got Kelvin. Okay, so this Kelvin will cancel with that Kelvin. So there's no units on the right side. So now let's go ahead and multiply that out. So that's negative 3007 times 0.00278. And it looks like it's negative 8.359. And that's equal to ln of P2 over P1. Okay. So we're getting there. We're almost there. The nice thing about this problem is it sort of leads you into what you're going to be doing when you take Chem 12 if you take that course. You do this type of mathematical operations quite a bit in there. Okay. So here's the situation now. We want to find P2. We do know P1. And we know the natural log, ln, is called the natural log. And it's a function. Here's what I'm going to do to kind of help you with this. There is a rule of logs, including the natural log. And the rule is if you have the log of a ratio, so see how I'm writing that as a ratio? That is equal to the log of the one in the numerator minus the log of the one in the denominator. Okay? So if we have ln of P2 over P1, that would be ln of P2 minus ln of P1. That's a nice, very powerful rule of logarithms. Okay. So now here's another rule. So that's one rule. The second rule is that if you have the log of the natural log of something equals a constant, n for constant, what you can do is use the exponential function to remove the natural log function. So the way you do that is you do e, that's the exponential function, to each side, e to the ln of a. What happens is, since the exponential function is the inverse function of the natural log, they essentially cancel each other. That's not the technical term for it, but that's effectively what they do. So if you have ln of something and you want to get rid of the ln, you do e to it, and that just gets rid of it. But it's not magic. It's not just like you can just erase it. You have to do the same thing to the other side. So you have to raise it e to the n. So you're doing it to both sides. Remember, like algebra, right? So if we do e to both sides, we now got rid of the natural log on the left side, but now we have an exponential function on the right side. Now, that's not a problem for us because calculators have exponential functions. E to the x is called, or exp. So we can use that to go through it. Okay. So now what I'm going to do is I'm going to apply that to this particular situation. We've got ln of P2 over P1, and then that's equal to minus 8.359. Okay, so I'm going to write it again up here just so that you can see it. So ln of P2 over P1 equals minus 8.359. So I'm going to use the exponential function. I'm going to use the second rule here. This will work a little bit better for us. So here's what I'll do. E to the ln of P2 over P1 is now going to be equal to e to the minus 8.359. But again, e to the ln, they effectively eliminate each other. So now on the left side, you just have P2 over P1. And that's going to be equal to e to the minus 8.359. Okay. Now, here's what we do. Evaluate this with your calculator. Okay. So here's how many of these calculators work. You'll see a function which is called ln, and then the second function above it is e to the x. Okay. So if that's the case, if sometimes some of the calculators will just have a function e to the x, and that's fine if you have that. But if you don't, look for the one that says ln, and then the second function will be above it usually, depending on your calculator, of course. So what you do is you enter in your number, minus 8.359, depending on your calculator. So make sure it's negative. And then you do your e to the x. So you hit your second e to the x, and then that's going to give you the number. So that is, I'm going to write it down in scientific notation, 2.343 times 10 to the minus 4. Okay. So now we've got P2 over P1 equals that number. Notice the negative went away. That's what happens when you do e to the x of a negative number, it becomes a number less than 1, but the negative is gone now. So now P2 over P1 is equal to this number. So that means we just have one more algebraic step to do. And that is to find P2. So I'm going to multiply both sides by P1. So P2 will be 2.343 times 10 to the minus 4. That's unitless times P1. Okay. So that would be 2.343 times 10 to the minus 4. And then P1 we said was 760. Okay, so P2, taking that number times 760 is going to be pretty small. It's only about 0.178 torr. Okay, this is unitless. This is torr. So our answer is torr. I imagine, is 3 sig figs reasonable? I guess 3 sig figs is probably reasonable. So think about this logically. What they said in this problem is that when the temperature was 360 Kelvin, very high temperature, right? The vapor pressure was 760, the boiling point. It was boiling at 360 Kelvin. Lower the temperature to 180. Now the temperature is much, much lower. The vapor pressure should also go much, much lower because remember the curve, right? It's pressure versus, it's a PT curve, goes something like that. So if the normal boiling point is here, you know, there's your 760. And this is your 360, go down all the way to 180, you're going to have a much lower pressure, a much lower vapor pressure. So in this case, it ended up being a little bit under a torr, or actually significantly under a torr. Okay, so that's called the Clausius-Clapeyron equation. And that equation allows you to be able to do these sorts of calculations. Let me save that one. And again, let me come back in here. Let me just remind you how I did that. P2 over P1 is equal to some constant. What I did was I used this rule, which is E raised to the ln of x is equal to E raised to whatever n is, right? E to the n. Well, I'm sorry, no negative. So if you've got, you know, ln of x equals n, x is equal to e to the n, okay? Because e to the ln of x is just equal to x. So that's what I did here. I said, look, I got a natural log here. I don't have a natural log there. So I said e to the ln of P2 over P1. That's going to be equal to e to the minus 8.359. The e and the ln, again, I wouldn't draw lines through. That's actually inappropriate to draw lines through there because you're not canceling like you would cancel x over x. These are inverse functions. It's kind of like this. If I said, what's the square root of x squared? And you said that the x, that's partially right? I mean, it's a little bit more complicated than that, but essentially that's the idea here. These are called inverse functions. The square root is the inverse function of the square. Or for those of you that have taken trig, the sine of sine minus 1 of x is just equal to x, right? You're doing the inverse function there. So same thing here, e to the ln, that's just going to give you P2 over P1, and then that's going to give you your small number, e to the minus 8.359. For those of you that have the other type of calculator, what you do is you do, you know, e, and then you put in your number, right? Sometimes you have to do that depending on which type of calculator it is. I like the TI 30X because you put in the number and then you hit e to the x. But if you're using that other type of calculator, then sometimes you have to do the function first and then the number, and then you hit equal sign. Okay. And there you go. All right. So that's the Clausius-Clapeyron. And there you go. Okay. So I have a couple of more topics to cover tomorrow, so I'll log in tomorrow and finish up a couple of topics on that from this section, because it's kind of a long section, and then that'll be it for the material. Okay, so have a great day.
Quick question.